Uh, this lecture is on concentrating solar collector. Let me first read out this text written over here, then I will explain concentrated solar collector with the help of figure 1 over here. Concentrated solar collectors are used to obtain energy at temperatures higher than those possible with flat plate collectors. The energy at high temperature can be obtained by increasing solar radiation intensity falling on the absorber surface. This can be achieved by using large reflective surface called concentrator or reflector to concentrate sunlight onto a small area, which is also called receiver or absorber. Now here in this figure, you can see that this parabolic shaped large surface is this. This is the concentrator or reflector. Uh, the inside surface is consist of a highly polished stainless steel surface, so that all the radiation which falls on this surface is reflected towards this side on this tube, and this tube is a receiver absorber surface. So all the radiation falling on this surface is now uh, coming onto this surface. So that means the energy is in a highly concentrated form is now falling on this surface, and some heat transfer fluid is made to flow through inside this absorber tube, so that the heat absorbed in this absorber tube can be transferred to some other place for some useful purpose. The reflecting surface focuses the beam radiation to the receiver only when the beam radiation means the radiation which comes directly from sun to the place in a question without changing its direction. So the reflected surface focuses the beam radiation to the receiver, that is this reflective surface focuses this beam radiation towards the receiver only when the beam radiation enters perpendicularly through the opening of the concentrator. So this is first condition, that the sun radiation, this is this is the cross section of this parabolic trough collector, one of the cross section. Now here this is the opening. So here you can see that the sun radiation is entering to the opening of concentrator in a perpendicular direction, like this. Okay, and receiver is placed at focal axis, and the second condition is that the receiver which absorbs this solar radiation should be placed in this on this point, perpendicular to this point. Hence concentrating collector should always be oriented towards sun by using sun tracking mechanism. So sun radiation should always enter perpendicular to this opening. That means this opening should be always be oriented towards the sun. That is why the concentrating collector are always equipped with the sun tracking mechanism, and the receiving surface should always be placed at this point. Otherwise, if it is placed at any other location, then the radiation will concentrate in on this direction and it will not fall on. It will not come on the absorbing surface, right? There are broadly two types of concentric collector, although there are some other types of as well, but mainly two types of concentric collectors are there. Parabolic trough collector. Trough means channel. Parabolic dish collector. So here in this diagram, a parabolic trough collector is shown. Trough means channel. So you can see that its its cross section is this channel is parabolic, but this has some channel. A parabolic trough collector is a line focusing type solar collector. Line focusing means here you don't have a single point as a focus. Here this complete line is a focus. So all the radiation falling on this surface at any point will be focused towards this line. The reflector is manufactured in the form of a channel or trough with the parabolic cross section. The parabolic trough shaped concentrator reflects direct solar radiation onto a receiver or absorber tube located in the focal line of the parabolic trough. An absorber pipe is placed along this line, and a working fluid, usually synthetic oil or water, or sometimes molten salts, are also used. So this fluid flows through these inside these absorber tubes. When the focused solar radiation fall on the absorber pipe, it heats the fluid to a high temperature. The solar radiation is thus transformed into a thermal energy in the form of sensible or latent heat of the fluid. Since the temperature reached in concentric collector is maybe as high as 200 degrees centigrade or 300 degrees centigrade, so in case the heat transfer fluid flowing through this tube is water, then obviously water while passing through this tube may be converted into this tube. So if there is friction, then the energy is absorbed in this fluid either in the form of sensible, that is in the only in raising the temperature, or may also be in the form of as a latent heat. This thermal energy can then be used to feed either industrial process demanding thermal energy, food industry, petrochemical energy, or in Rankine cycles to produce electricity with steam turbine and solar thermal power plant. You see, you have studied conventional thermal power plant in applied thermodynamics course. So in conventional thermal power plant, the the heat energy is coming from the combustion of the fuel, where here the in case of solar thermal power plant, the energy is this sun energy, radiation energy coming from the sun. Rest all accessories, all components working in case of solar thermal power plant is exactly like the conventional fossil fuel based thermal power plant, and the system also works on the Rankine cycle, except that in case of in this case sun energy is used. Now, next is parabolic dish collector. In case of parabolic dish collector, this concentrator is of a dish shape, exactly the dish that we use in our households to receive the TV signals. So a parabolic dish collector is a point focusing type solar collector. So it is a point focusing because all the radiation is now focused to a point. The reflector is formed into a paraboidal shape by stamping them out from thin sheet metal. The paraboidal dish collects the incoming solar energy directly from the sun and concentrates or focuses it on a small focal point area positioned in front of the dish. The parabolic dish solar dish is covered with many small mirror reflectors all around its shape to help concentrate the thermal energy into a single focal point where where the heat absorber is located, producing more overall thermal energy per square meter of the dish. So here you can see that in this reflecting surface, the reflecting surface is not a highly polished, stainless steel surface. Rather, the inside of this dish is covered with a small size mirrors. So this total then uh, these mirrors makes a large dish type of reflecting surface. These highly polished mirrors can reflect more than 90% of the sunlight that hits them, increasing the efficiency of the dish by more than 20% compared to the parabolic draft collector. So that means parabolic dish collectors are more efficient than the parabolic draft collector. Mirrors are generally used instead of single highly polished discs because they are relatively inexpensive, can be easily cleaned, and last a long time in an extreme outdoor environment, right? Making them an excellent choice for the reflective surface for a solar disk collector. Also, individual mirrors can be easily changed if damaged. A parabolic disk system uses dual axis tracking to follow the sun across the sky. In case of a parabolic trough collector, only a single axis tracking is required. Whereas in case of parabolic system, dual axis tracking is required. So so that means the tracking system for the parabolic disk collector is relatively complex and has costly than the uh, sun tracker for the parabolic trough collectors. Sun Echo, the solar receiver can be as simple as a small evacuated tube because it is a point focus, so a small evacuated tube should be there, or the receiver may be a more complex solar heat engine such as Stirling engine. That means the heat absorbing side of the Stirling engine will be pointed towards this reflective surface so that all the radiation is reflected towards the heat absorbing side of the Stirling engine. Due to very high temperature at the focal point, a thermal oil type fluid is generally used instead of water inside the receiver, which transfers the intense heat created by the focusing sunlight on the receiver. Now the basic terms and definitions related with the concentrating collector. Concentrator, I have already explained, it is a large reflective surface which is placed between the source and radiation to concentrate the solar radiation flux onto the receiver. Receiver is the component of a system, entire solar thermal system, which it receives the energy and absorbs the energy. So it receives, absorbs, so radiant energy and convert it into a thermal energy or electrical energy. This can be either a heat absorber surface to convert solar energy to thermal energy, or a photovoltaic cell to convert sunlight to electrical energy. So here, because we are not in doing the photovoltaic studies, so we are interested only in this first case. That is, the receiver is consisting of a heat absorber surface. In the first case, the solar radiation is absorbed to heat a medium known as a heat transfer fluid, which transfers that absorbed energy from for some use applications such as conversion of water into steam in the generator or the boiler for the solar energy based thermal power plant. In the second case, light causes photovoltaic effect in the material of the solar cell which generates the electrical in case of photovoltaic cell, right? So because this is a heat transfer based course, so we are interested only in the first case. Now, in the first case, the receiver consists of cylindrical shaped absorber tube surrounded by an evacuated cylindrical glass cover as shown in figure. So let me explain this figure. So here this is a metallic tube. Inside this metallic tube, a heat transfer fluid flows, which transfer the heat absorbed in this tube. The outer surface of this heat tube is black painted, hence is absorbed for the solar radiation, and this tube is has a transparent glass covering envelope to reduce the radiative and convective losses from the heat absorbing on this absorber surface. And this annular space is completely evacuated, has a vacuum, so in order to significantly reduce the heat losses from the absorber surface to the surrounding. Now here di is the inside diameter of the absorber tube, d naught is the outside diameter of the absorber tube, l is the length of absorber tube. Normally the length of the absorber tube is equal to the length of the parabolic trough. In case of parabolic, the length of the parabolic trough is equal to the length of the absorber tube. Absorber tube surface is pi d naught L, that is outside diameter, because the energy is absorbed on the outside diameter or outside surface. So pi d naught L is the surface area of the absorber tube. DGC is the diameter of this cylindrical glass cover. So diameter of the cylindrical glass cover is DGC. Next parameter is aperture. The aperture of concentrator is the opening through which solar radiation enter the concentrator, and the area of this concentrator opening is called aperture area. So this opening of this concentrator, radiation is coming from, say, above. So this opening through the radiation enters is called the aperture, and this aperture area, W into L, is called the aperture area. But here you can see that this opening is somewhat restricted due to presence of this absorber tube. So the effective aperture area, that is the effective area through which the solar radiation enters into the concentrator, is total this concentrator opening area W into L minus area blocked by the receiver, which is DGC into L, right? Now, next is concentration ratio. Concentration ratio is the ratio of the effective area of the aperture to the surface area of the aperture. So this is called the concentration ratio because the energy which is energy flux which is falling on this absorbed surface is concentrated or enhanced by a factor equal to C. Heat loss from absorbed surface. The heat loss from the unit area of the surface to surrounding can be calculated as UL into TAB minus TAB. The heat loss from the surface, the heat loss from here to the surrounding. So this heat loss can be calculated per unit area by using this equation, where UL is the overall heat transfer coefficient from the absorber surface to the surrounding. So TAB is the surface temperature on the surface of this absorber tube. T is the ambient temperature. So QL is equal to UL, TAB minus TA is equal to temperature difference across this tube, TAB minus TA, upon this resistance R1 plus R2, right? Convective resistance between R1 is convective resistance between this tube surface to the glass inside glass inner surface, and R2 is the convective heat transfer from between outer surface of this glass inner to the surrounding. Now absorb the radiation flux. Now in case of concentrated collector, the absorbed radiation flux, that is the energy which is absorbed on the absorber tube or absorber surface, is defined in a somewhat different manner than that what is defined in flat plate collector. The purpose is to simplify the analysis of the thermal analysis and to find the final expressions in a more simplified form. So for the sake of simplicity of thermal analysis of concentric collector, the solar radiation absorbed by absorber tube is expressed in terms of solar energy absorbed by absorber tube per unit time, because it's a flux of per unit time per unit area of aperture. So this is the aperture. and this is known as absorbed radiation flux. Let me explain it with some example. Say S is 500 watt per meter square for concentrating collector. That means this 500 is absorbed solar radiation per unit time. That's a watt per unit effective aperture area. Say for example, effective aperture area is 2 meters square. Effective aperture area means total this opening area minus area blocked by this absorptive is say 2 meters square. And if the value of S equal to 500 watt per meter square for that means the total energy absorbed by this absorber tube per time will be 500 into this effective aperture area, this much. So in case of plate collector, the S is defined as the absorbed radiation per unit time per unit absorber area. Whereas in case of concentric collector, S is defined as absorbed energy on the absorber tube per unit time, but not per unit surface area of this tube, but per unit area of effective area of effect aperture area, right? Now, thermal analysis of concentrating collector. The procedure for analysis of concentrating collector is similar to that of flat plate collector. So here we are not, repeating the things because the process is exactly the same. What we are interested in to know the final end results that we are going to use in designing or solving the problems. So following the same procedure, the mathematical expression of collector efficiency factor, collector heat removal factor, and useful energy gain for the concentrating collectors are as follows. These are the important, key output parameter that we obtain from the heat transfer analysis. So in the first column, I have compiled the results for the flat plate collector, and in the second column, I have compiled the results of that we can obtain by doing the thermal analysis of concentrating collector. So F1, that is collector efficiency factor, this I have already explained this in the earlier video for the flat plate collector. Now in case of the concentrated collector, F1 expression for F1 is like this: 1 by UL. UL is overall heat loss coefficient from the absorber tube to the surrounding that I had just explained in last page, divided by 1 by UL plus DO upon HFI upon DI. DO is outside diameter of the absorber tube. DI is inside diameter of the absorber tube. HFI is the heat transfer coefficient inside the tube. DO upon 2K. K is thermal conductivity of the tube material. Natural log of DO upon DI. Now next parameter is collector heat removal factor. Now in both the cases, that is for flat plate collector and concentrated collector, the expression is exactly the same. ZF1 1 minus exponential of minus 1 by Z. The only difference is in a small difference in this Z value. In case of flat plate collector, Z is m dot Cp upon AC F1 UL, where AC is the collector area, that flat surface area. In case of flat plate collector, the absorbed plate is flat in nature, where in this case Z is expressed as m dot Cp, more or less is the same. AAB F1 UL, F1 UL is also there. So here the absorber surface is the surface area of the tube, where in flat plate collector absorber surface the collector area surface. So here we have written AC, here I have written here written AAB. Now next important parameter is the useful energy gain. This is the expression for useful energy gain. Heat removal factor, which is equal to FR, which is equivalent to the effectiveness or efficiency of heat exchanger multiplied by the maximum useful energy gain that can be obtained when the heat losses from the absorbed surface to the surrounding is minimum. So this is the expression that we have obtained for the flat plate collector. Heat removal factor, which is equivalent to the effectiveness of heat exchanger into maximum useful energy gain, which can be obtained if the entire plate area has a temperature equal to the inlet flue temperature. Now, in the case of concentrating collector, this expression is again FR into Qmax, where FR is this. Now, inside this parameter, there is a slight difference. AAP is aperture, effective aperture area. AAB is absorptive surface area, right? And here S is solar radiation absorbed per unit absorbed plate area, whereas here S is absorbed solar radiation per unit effective aperture area. Now I have solved a question for you to give some direction how to solve a problem. Now this is a question. This question is on parabolic trough collector. The collector is parameter of 10 meter long, that is L is 10 meter, and it's 2.5 meter wide, 2.5 meter wide, and perpendicular to this, this page, the length of the collector is 10 meter. The ambient temperature is 10 degrees centigrade, right? And absorbed radiation frequency 430 watt per meter square. Again, it is 430 watt of energy absorbed per effective aperture area. The absorber is a cylindrical tube with its outer surface painted black and surrounded by evacuated cylindrical glass cover. So here you can see this is painted black outside surface is surrounded by a glass envelope, which is shown as a green color here. The absorber has a diameter of 60 mm and the cylindrical glass cover has a diameter of 90 mm. So this 90 mm, this 60 mm absorber diameter is the outside tube diameter, and this cylinder glass cover has a 90 mm. That means this DGC, this glass envelope diameter is 90 mm, and outside tube diameter of the absorber tube is 60 mm. The collector is designed to heat a fluid entering the absorber at 200 degrees centigrade. So inlet fluid temperature is 200 degrees centigrade, which is quite high. That means the heat transfer fluid is being recirculated, right? At a flow rate of 0.0537 kilogram per second, the fluid specific heat is 3.26 Cp is this. The Cp of the heat transfer fluid flowing through this tube. Heat transfer coefficient inside the HFI is 300, watt per 300, UL is 10.6. The tube is made of stainless steel. K thermal conductivity of the tube material is 16. Wall thickness is 5 mm. The wall thickness of the tube is 5 mm. That means if the outside diameter is 60 mm, that means the inside tube diameter would be 60 minus twice of the wall thickness, that is 50 mm. Estimate the useful again and exit fluid temperature. So all the given dimensions are written over here. First we will find the surface area of the absorber tube, which is pi d naught L. D naught is 0.06 meter, right? Aperture area development, this formula, this comes out to 24.1 meter square. Then we will use the collector heat removal formula F1. Then F1 is used in this expression FR, where Z is m dot Cp AB F1 UL. So Z comes out to be 9.15, which has to be put over here. Then FR becomes 0.91. Then we will use this expression for the specialty collector. The energy gain comes out to be 5980 watt. So we also know that the useful energy gain is also given by the thermal energy increase of the fluid flowing through the tube, which is m dot Cp TU minus TFI. So finally, we get the outside tube temperature as 234 degrees centigrade. So that's it about this lecture.